Is about dipole. What is a dipole? Dipole is two equal and opposite charge minus q and plus q separated by a distance of 2a is known as a dipole. What is a dipole moment? A dipole moment is either of the charge. The dipole moment is represented by capital P. It's either of the charge into separation between them. It's a vector because 2a is a vector. And the direction of the dipole moment is from negative to positive. Just remember that it's always from, electric field will be from positive to negative, but the dipole moment is from negative to positive. So the 2a is a vector, so dipole moment is a vector. Its SI unit will be coulomb meter. Okay, that's dipole moment. Next is how to find the electric field on an axial line of a dipole. Axial line of dipole. So let's draw a dipole, which is this is like minus q and a plus q. So you got a separation between them is 2a. You got to find a electric field at a point P, which is lying on axial line, whose position vector is r from the center. This is a and this is a. So this gap therefore is r minus a, and this whole distance therefore is r plus a. So you got to find the electric field at a point P. This is negative charge, and let's call this end as a and this end as b. The electric field due to a will be in this direction, EA, because it's negative charge. Positive charge due to positive charge, EB will be in this direction, and EB's effect will be greater because plus Q is located closer to the point P. So the net electric field is EB minus EA. And since you've taken the vectors into account, you can just take, you can ignore the negative signs of the charges, and you can write the EB and EA, which is what is EB? Is this electric field that exists between this and this. It's 1 by 4 pi epsilon naught into Q by r minus a the whole square, because that distance here is r minus a. This whole thing is r and this thing is a, so this distance is r minus a, minus 1 by 4 pi epsilon naught into this q. You're not supposed to take minus q, you're supposed to take only plus q because you've taken the directions into account already. So 1 by r plus a the whole square, because the whole distance will happen to be and this is r and this is additionally a, so r plus a the whole square. So then what is common here is 1 by 4 pi epsilon naught is common, q is common, 1 by r minus a the whole square minus 1 by r plus a the whole square. So then you get this can be written as k into q into LCM is r square minus a square the whole square, so it will become r plus a the whole square minus r minus a the whole square. So then therefore this, when you expand this, you will get a 2ar and 2ar, which will make it 4ar. We'll make it 4ar by r square minus a square the whole square. This is your electric field along an axial line, the magnitude of it. But having said that, you already know dipole moment is either of the charge into separation 2a. So q into 2a, you have to write this as 4a as 2 into 2a. So it will become k 2 pr by r square minus a square the whole square will be the axial line's electric field. Supposing a case study where r is much larger than a, then you can ignore the a, and then formula will become k2p r by r to the power 4. When this and this get cancels, go k2p by r cube. This is the value of the electric field along an axial line of a dipole, considering r is much larger than a. Okay, so then what's this direction? Let's see. EB's effect is greater than EA's effect, so net electric field will be along EB and along the direction of the positive x-axis. That's the direction of the net electric field, E axial at any point P on the axial line of the dipole. Next is E equatorial. Equatorial line. What is the electric field on the equatorial? Equatorial line of dipole. What is the electric field? So let's take a dipole again. This is minus q and a plus q. So you're going to consider a point on the equatorial line. You know that at this point, this negative charge will have an electric field in this direction. Let's call this as A and B. So your UEA will be in this direction, your EB will be in this direction. Okay, so then you can complete this as a triangle. The position vector at any point P will be always at distance of r from the center. Dipole is total length 2a, so this side is a and this side is a, hence the hypotenuse is root of r square plus a square. Here also hypotenuse is root of r square plus a square. And the AB and EA will have a resultant vector which will be in this direction. Okay, let me tell you that if you have a vector like this, it will have components, vertical component and a horizontal component. Considering that this is theta, and this is also theta, then the corresponding angle, this will also be theta, interior alternate angle, this will also be theta. So then therefore that EA the EA which is in this direction will get broken down into an EA cos theta and an EA sin theta. Similarly, you have an EB which is in this direction, which will get broken down into an EB cos theta and an EB sin theta. And can you see from here the vertical components will cancel off, the sin theta component will get cancelled off, only the horizontal component will get added, only this horizontal component will get added. So therefore it will be EB cos theta plus EA cos theta. Both of them are pointing towards the negative x direction. So then both of them have to be added, and you have a cos theta which is common. You have an EA plus EB. So thus you have a EA plus EB into cos theta. From this triangle, any triangle you can write cos theta is adjacent, which is A, by hypotenuse, which is root of r square plus a square. So substituting that, what is EA? EA is the electric field due to this charge. You shouldn't take the minus into account. 1 by 4 pi epsilon naught. Should not take the minus into account. So it's 1 by 4 pi epsilon naught into q by distance the whole square, root of r square plus a square the whole square, where root and square will get cancelled, plus 1 by 4 pi epsilon naught into EB is also q. Okay, whatever, that is q. The charge q by root of r square plus a square the whole square, which is r square plus a square. So it's adding up twice. So it will become 1 by 4 pi epsilon naught into 2q by r square plus a square. In addition, you have a cos theta, which itself is this. So you have to include this, which is a by root of r square plus a square. In both the places, a by root of r square plus a square. You know, a 2q is nothing but a dipole moment P. You can write this as k, that is P by r square plus a square, the whole to the power 3 by 2. That will be the electric field along an equatorial line. Okay, so then considering that r is much larger than a, then the E equatorial, a can be ignored, you will get kp by rq. Okay, so that's about it. This is an electric, and its direction is again along negative x direction. That shows that this is equatorial line and the axial line is positive x direction. So the angle between the axial and equatorial itself is 180 degree. And axial, E axial is in this direction and E equatorial is in this direction. So the angle between them is being 180 degree. So then if they ask you what is the angle between them, you know, they are anti-parallel. Okay, so then that's about the electric field. And then what happens to the dipole when it's placed? How is uniform electric field represented? I'll tell you, a uniform electric field is represented like this. This is how a uniform electric field is represented. A non-uniform electric field may be like this, where the electric field is greater here, the electric field is lesser. EA is greater than EB. Because lines are closer shows that electric field is greater here. So then this is about how to draw a uniform electric field. Consider a dipole which is minus q and a plus q here, making an angle theta with the electric field. Okay, so you know that you want to find the perpendicular distance. Then you know that sine theta, this distance, this is 2a, you know. The dipole's length is 2a. So sine theta is equal to opposite by 2a. So opposite side itself is 2a sine theta. Thus you get this length, perpendicular distance to be 2a sine theta. Okay, where is the dipole? The dipole is here, which is minus q plus q. Okay, you know that due to minus q, there will be E is equal to F by Q, F is equal to E into Q, will be negative direction because charge is negative. Positive charge, so E is E into Q in positive direction. So you have two forces, both are equal but negative, opposite sign. Okay. So now the whole question is, if a dipole is placed in an electric field, it is going to experience torque. What is torque? Torque is force into perpendicular distance. R cross F. Torque is equal to R cross F, you all know. So here you can write torque is equal to R cross F, and write torque is equal to force into perpendicular distance. E is equal to F by Q, F is equal to E into Q. Perpendicular distance is 2a sin theta. The fact that 2a q itself is P shows that it's EP sin theta, or it's a cross product of P and E. Dipole moment and electric field is cross product of this is what is torque. And you know, case study, theta is equal to 90, sin theta will be 1, and torque will be equal to EP, which is a maximum torque maximum. And theta is equal to 0, then the torque itself will be 0. These are the two case studies you have. Next, this is about what happens when a dipole is placed in uniform electric field, and it produces a torque, and how does a torque produce, what is the value of the torque, dipole moment cross electric field. Then is about potential energy. Is about potential energy of a dipole. Energy of dipole in an electric field. Of dipole in an electric field. In a uniform electric field as usual. Okay, so then you're going to find the potential energy. Potential energy is similar to work done. Work done is force into displacement, but here it's for dW is not force, it's torque, because there's rotational force, and displacement is not just ds, it's d theta. So dW is equal to torque into d theta. You all know torque itself is Pe sin theta. From here you can substitute torque is equal to Pe sin theta d theta is dW. On integrating both sides, take the Pe out, dipole moment and electric field out, integration of sin theta into d theta. If you integrate sin theta, you will get minus cos theta. Okay, you should know that integration of sin theta is minus cos theta. So then minus Pe cos theta. Okay, integrated from theta 1 to theta 2. You're going to integrate it from theta 1 to theta 2, so you'll have theta 1 to theta 2. So therefore the formula will be minus Pe cos theta 2 minus cos theta 1, upper limit minus lower limit. If you take the negative sign inside, it will become Pe cos theta 1 minus cos theta 2. Okay, suppose this will be your potential energy. Okay, suppose we'll consider that the dipole initially is at an angle, this electric field is at an angle 90 degree, because that's when it experiences maximum torque, right? So let's assume that theta 1 is at 90 degree. Let's assume that it's moving through an angle theta, that is theta 2 is theta. Then the formula of potential energy will become, this will become 0, cos 90 is 0, and therefore we'll get a minus Pe cos theta. So this is the formula I would like you to remember, it's minus Pe cos theta. So here comes a stable and unstable equilibrium part. Okay, there's a case study. The case study is when case 1, when theta is equal to 0. When theta is equal to 0, your potential energy is minus P, because cos 0 is 1. So this is negative. When theta is equal to 180, cos 180 is minus 1, your potential energy is maximum, it will be Pe. But here the potential energy is minimum. The potential energy is maximum will be most unstable position always. Can you imagine a water tank which is located on the terrace or in your house? It has got higher potential energy, but the water gets filled, it flows from higher potential to lower potential because it's unstable. So anything which has got maximum potential energy always stands for an unstable equilibrium, just for you to remember. And therefore this stands for a stable equilibrium. So what is the meaning of that stable equilibrium? Like supposing in if the dipole is in this position, which is a stable equilibrium position, that is when theta is equal to 0, which means the electric field is like this, and the dipole is also in the same direction. I mean, it's making an angle 0 with the electric field. Then slightly if you rotate, if you rotate it also, it will come back to its equilibrium position. However you disturb it, it will come back to its original position. But unstable is when you disturb, it will not come back to its equilibrium position. That's what it means. Just one small note on it. Okay. So this completes the stable and unstable equilibrium part, which is a very, very important question. Okay. Next is, of course, therefore the conclusion is when a dipole is placed in a uniform electric field, it undergoes a torque. Yes. And a torque will be 0 if theta is equal to 0, but torque will be there in generally otherwise. Okay, so, or theta is equal to 180 also, there will be no theta is equal to 0, theta is equal to 180 also, there will be no torque. Okay, so then there will be generally a dipole placed in an electric field making some angle other than 0 and 180 will experience a torque. The torque is equal to Pe sin theta, and the potential energy is minus Pe cos theta, and the potential energy is maximum stands for unstable equilibrium, which is when theta is equal to 180 degree, and theta is equal to 0 stands for stable equilibrium position. Okay, now therefore a dipole in an electric field produces a torque, whereas in a non-uniform electric field such as this, as I told you, the electric field at the point A is greater than the electric field at the point B because closer are the field lines. In this case, if you place a dipole, it will not only experience a torque, it will also get it will also move in a straight line. Why? Because there will be a force in this direction, minus q and a plus q, and there will be a force in this direction where it's A into Q, and this will be EB into Q. They are not just E into Q because the values are different, and EA is greater than EB. So this force will be greater, and therefore the torque, the dipole will also move along with experiencing a torque. In addition to rotational motion, it will also have a rectilinear motion, linear motion. Okay, it will go like so it will have both kinds of motions in a non-uniform electric field. So that's very, very important. Why? Because of the values of the electric field being different, the force on both ends will also be different. So then next is some numerical related to dipole. See, there's another one important question which will come. Supposing you have a metallic conductor and you have a positive charge, draw the field lines. It will emanate from positive and be normal to the surface. Emanate from positive, normal to surface. Emanate from positive, normal to the surface. This is how the electric field lines will be. And because this is positive, the near end will acquire negative charge and the far end will acquire a positive charge, and still it will emanate from positive. So this is how we draw the electric field lines for a conductor and a positive charge. Supposing it's a negative charge and there's a conductor, it will terminate at the same kind of diagram. It has to be normal to the surface, normal to the surface, and normal to the surface, compulsorily normal to the surface. Okay, but it will terminate at the negative, which you all know. And so then therefore this near end would have become positive, the far end would have become negative, and so then the electric field lines, this is the way you should draw of the electric field lines for a positive charge and negative charge into a conductor. Okay, this is very important. The next is define electric flux. What are electric flux? Electric flux is represented by like this, and electric flux is integration of E dot ds over a closed surface. So it's like a surface integral of an electric field over a closed surface. A surface integral of electric field over a closed surface. You understood? E dot ds. This is what is flux. Flux is a definition for this. Is surface integral of an electric field over a closed surface is known as a flux. In simple words, you can also say number of electric field lines. A number of electric field lines is what is referred to as flux. The total number of electric lines of force passing through unit area is also called flux. Supposing there is a unit area like this, the number of field lines passing through this unit area is also known as flux. But the actual definition being a surface integral of an electric field. Surface integral of electric field over a closed surface is what is called a flux. You have to memorize this. Simply the number of lines of force passing through unit area of the surface is known as flux. Then as Gaussian's theorem. Gauss theorem. According to Gauss, he said that flux is nothing but Q by epsilon naught, where Q is the source charge. Supposing you have an electric field which is produced by the source charge, the flux that is emerging out, the electric field lines, if it's positive charge, will emerge out. The flux is these lines which is coming out normal to the surface. Okay, so then the enclosed source charge by epsilon naught as you know is the permittivity, absolute permittivity. So then therefore, according to Gauss theorem, flux is 1 by epsilon naught times enclosed charge. That's the way you are going to define it. So that completes your therefore Gaussian's equation. What will be Gaussian's equation? You have to equate both of this. This is equation 1, this is equation 2. So both of them are flux. The hence integration of E dot ds over a closed surface can also be written as Q by epsilon naught, and this is the Gaussian's equation. Hope you're clear. This is Gaussian's equation. We can arrive at the Gaussian's theorem using Gaussian's equation. So you take this integration of E dot ds. You already know E is 1 by 4 pi epsilon naught into Q by r square into ds is the surface area which is getting integrated over. See, supposing it's a Gaussian's is a spherical surface. Imagine a Gaussian surface to be a spherical surface. It's 0 to 4 pi r square. So when you integrate in 1 ds, it will become s. So 1 by 4 pi epsilon naught into q by r square into s itself is 4 pi r square. 4 pi get cancelled. R square get cancelled. Thus you get q by epsilon naught. So thus you can arrive at a factor that the flux is q by epsilon naught using Gaussian's equation. Okay, so then that completes it. It's not very important, but just for you to know. But you should know this is what is Gaussian's equation. What is Gaussian surface? What is this Gaussian surface? Gaussian surface. It's an imaginary surface. An hypothetical closed surface is an imaginary surface. Supposing there is there's a charged particle, a spherical charged body. This is a spherical charged body. Can you imagine that you will have a Gaussian surface which is a closed surface around this charged particle, around the charged body. It's a closed surface. It's a hypothetical closed surface. It's an imaginary surface. என்ன சொல்றது, இப்போ சாமி படத்துலலாம் அந்த ஒளி வட்டம் இருக்கும்ல, சாமியோட தலையை சுற்றி ஒளி வட்டம், that ஒரு பல்ப் எடுத்ததுன்னா அது outside the bulb there be radiations, that ஒளி வட்டம், that kind of a spherical surface is what is called Gaussian surface. It's a hypothetical closed surface enclosing a charge is what is called. So hypothetical closed surface or an imaginary closed surface enclosing a charge is what is called Gaussian surface. So then different charged body can produce different Gaussian surfaces. A spherical charged body can produce a spherical Gaussian surface, correct? So then line charge, supposing it's a line charge, it will produce a spherical Gaussian surface. Because this will have electric field lines like this. Suppose it's positive charge, and can you see the Gaussian surface is this surface which is perpendicular to the electric field lines. Okay, so then similarly your electric field lines for the line charge will be like this at all points, and it will form a cylindrical Gaussian surface. The Gaussian surface will be an imaginary cylinder. For a line charge will have a cylindrical Gaussian surface. So similarly, supposing you have a plane sheet, say a plane sheet like this with positive charges, then electric field lines will emanate from positive. It will also emanate from positive. The charges resides only on the surface. Okay, any charge always resides only on the surface of the metal. So then therefore the other side will also have positive, and so then it will emanate and it will form an imaginary cylinder, and this becomes a Gaussian surface for a metal sheet. So like that your Gaussian surface can take different imaginary shapes. Okay, so the next is so we have numericals based on it. So here comes a few numericals based on the flux and Gaussian surface, etc. So example 57, let's go through example 57. You have an electric field which is 6I plus 3J plus 4K. Calculate the electric flux through the surface of area 20 units. Area is given to be 20 units in YZ plane. Okay, supposing this is x-axis and this is y-axis and this is z-axis. Okay, suppose you have an area of 20 units in YZ plane, not in XY plane. So you have an area in YZ plane. You know that in physics area is always area vector which is normal to the area. This is a very important point you should understand. If you have a surface like this in XY plane, the area is 20 units, but the area vector will be along x-axis. When a plane is lying on YZ, then its perpendicular will be along x-axis, and x-axis represents I cap, and therefore the 20 units should be written as area vector to be 20I. Okay, that's very necessary. YZ plane means it's normal. There is area vector will be perpendicular to the plane which is along x-axis, which is 20I. So then they ask you to calculate flux. Flux is nothing but E dot ds. Electric field is 6I plus 3J plus 4K. It's given, and the area vector is 20I. So you can only dot an I and an I. So then therefore it's 120. That will be your flux. 120 units the flux. Okay, so then that's what it is. Let's go to next sum. Next is sum. Okay, next is sum. A circular plane sheet is example 58. A circular plane sheet of radius 10 centimeter is placed in uniform electric field of 5 into 10 to the power 5 Newton per Coulomb, making an angle 60 degree with the field. The electric field is what is making the circular plane sheet of radius 10 centimeter is placed in such a way that it's making an angle with the field. The sheet is making an angle theta with the field is 60 degree. The sheet is making an angle, sheet and the electric field. But you don't need the angle between sheet and the electric field. You need the normal to the sheet and the electric field, because E dot ds is a ds vector. That E dot ds is always a ds vector, and ds vector is normal to the surface. So if sheet is there, its normal is what you have to take. So if sheet and the electric field is making an angle 60 degree, the normal and the electric field will make an angle 30 degree, 90 minus 60, 30 degree. So then when you want to calculate flux will be E dot E ds cos 30. You know electric field 5 into 10 to the power 5 into ds vector. ds itself is area, which is a circular field. So circular plane sheet, which is pi r square, pi into r square into cos 30, and what's cos 30's value, you just substitute, and then you get 1.36 into 10 to the power 4, and the SI unit of flux is Newton. Units you can write units, but you have to write the SI unit, which is Newton meter square per Coulomb. Newton meter square per Coulomb. That is the unit for SI unit for flux. Okay, so let's go to next question. The next question that I would like to teach you is the example 62. Calculate the electric flux through each of the 6 faces of the closed cube of length L if a charge Q is placed at the center. So that's for A, section A. So you have a cube. A charge Q is placed exactly at the center, at the geometric center. You know, electric field lines will emanate from positive charge, so it will have electric field lines and also be normal to the surface. It will come out from all directions. Electric field will come out even inward and outward. Can you imagine? It will come in all directions along all the 6 faces. So then the flux, the question is about what is the flux through each phase. You know, there are 6 phases totally, and flux is generally Q by epsilon naught is a total flux coming out of this cube. So through total flux, then through one of the phases means you have to just divide it by 6. So that there are 6 phases, so the flux through one phase will be Q by 6 epsilon naught. That's one question. The other question would be, supposing there is a cube and the charge particle is placed at the vertices, at this vertex. Okay, so then imagine another cube which is placed adjacent to it. You have to draw another cube like this, then another cube on the top, behind it also. No, behind this there has to be another cube. On the top also another cube. So you have to build like this. I don't know how to draw. So then this you have like 4 cubes in the front and 4 cubes in the back, so that this will be exactly at the geometric center. And you know the electric field lines will emanate in all directions along all phases and normal to the surface. And then how many sides would it have? Outer surface. On the front you will have 4. On this, and it will have 6 sides, so 6 4s are 24 faces it will have. And so the flux out of one phase, that is just this phase alone, will be Q by 24 into epsilon naught. So that completes this question. So next question is the 63rd question. The electric field component in figure 1.88, there has been given a figure, can you see, where Ex is given to be alpha into Ex to the power 1 by 2. Ey is equal to Ex is equal to 0, where alpha is given to be 800 Newton per Coulomb meter square. Calculate the flux through the cube. Flux is E dot ds, correct? You know the flux is E dot. Okay, let's look at the diagram first. The diagram goes like this. This is x-axis, this is y-axis, and this is z-axis. They have drawn a cube here. They're given a cube here like this. They've given a cube like this. They've given the side of the cube is A. Length of the side of a cube is A. And they've also given that from the origin it's at a distance A. It's all given. Okay. And what else is given? And A is also equal to 0.1 meter. That's also given. So electric field component in this diagram, or Ex is equal to alpha into x to the power 1 by 2. E by Ez is equal to 0. There is only, which shows that the electric field lies only along x-axis. The electric field is not along y-axis or z-axis. Okay, so the electric field is along x-axis only. And it's given by alpha into x to the power 1 by 2. Calculate the flux. Okay. You know that, let's look at the left face. This is the left face. Okay, and you will have alpha into x to the power 1 by 2. Depending on this distance is where x is nothing but the position. At this position will be A. There will be an electric field Ex in this position, which will be alpha into A to the power 1 by 2. Correct? Alpha into A to the power 1 by 2 will be the electric field at this position. What about the right face? Let's call this right face, and here this is electric field on the left and it's electric field on the right, which will be alpha into what distance would it be? It's A plus A, 2A the whole to the power 1 by 2. So this is the value of the specific electric fields on the left and the right. Okay, and you know that the flux for the left face, flux is E dot ds, which is EL dot ds vector, EL dot ds vector, which is EL ds cos theta. If you remove the vector, they have to include a cos theta. And you know, EL is, let it be EL, and ds itself is A square, the surface area of the left face, into cos theta is cos 180. Why it's 180? The electric field's direction, say the electric field's direction they've given is along x-axis, which is like this. So if the electric field's direction is like this, the area of the left face is going to be like this. The angle between them being 180, and cos 180 is minus 1. So you will get a EL A square. And you want to calculate EL, you have already calculated it. It's alpha into A to the power 1 by 2 into A square. So you just consolidate this. You will get some answer, which is alpha into A to the power 3 by 2. Alpha into A to the power 3 by 2. No, not 5 by 2 I think. Yeah, 5 by 2. A to the power 5 by 2. That will be your answer for the left face. Let's do it for the right face. This is flux on the left, this is flux on the right, which is E right into ds vector, which is E right in ds into cos theta. When remove the vector, theta here will be, you know, the electric field is going to be in this direction. The ds vector, the area vector, is also going to be in this direction. The angle between them being 0, theta can be 0 here. So it's ER ds cos 0 is just 1. So it's ER into ds. You already know what is ER. It's alpha into A whole to the power 1 by 2 into ds itself is A square. So then consolidating is alpha into 2 to the power, it's root 2 into A to the power 1 by 2 plus 2, which will be 5, A to the power 5 by 2. So that will be it. But here it's cos 180. So then you will have a negative sign here, whereas you will have a positive sign here. So this is the flux through the left and this is the flux through the right. So the net flux, therefore, you just have to add both the flux through the left plus flux through the right, which will be minus alpha A to the power 5 by 2 plus alpha root 2 A to the power 5 by 2. So then in this, what is common? You know what is alpha? Alpha stands for 800. It's been given that alpha is 800. So you take 800 out, and you also can write A to the power 5 by 2, which is 0.1 is A. So 0.1, the whole to the power 5 by 2 is common. And then you have a root 2 plus 1 or a root 2 minus 1. A root 2 minus 1. Thus you calculate this, you get 1.05 Newton meter square per coulomb. This is a very, very important board exam question. Okay, so then let's go to next sum. no, then that is not over. The sum is not over because they've just not asked only the flux here. They seem to have asked the charge within the cube. You know, flux is equal to Q by epsilon naught. So charge is flux into epsilon naught. Flux it's 1.05 and epsilon naught is 8.854 into 10 to the power minus 12. So then if you multiply these values, you will get your charge, which has to be 9.27 into 10 to the power minus 12. That coulomb, that will be the charge. Okay, that completes the sum. Next, let's go to example 64. Example 64. The electric field is uniform and in positive x direction. Okay, so they've given that its electric field is in positive x direction. And with the same magnitude in the negative x direction. Oh, an electric field is uniform and is in positive x direction for the positive x axis, and with the same magnitude in the negative x direction for negative x. So electric field will be negative for the negative x axis and positive for the positive x axis. Okay, so then the value is given to be, E is given to be 200 I Newton per coulomb when x is positive, and E is equal to minus 200 I when Newton per coulomb when x is negative. So let's the right circular cylinder of length 20 centimeter, radius 5 centimeter has its center at the origin and its axis along the x-axis as shown in the figure. Okay, let's draw the figure here. This is the axis. You have a cylinder which is located like this. This is the origin. So you have a positive x-axis here where the electric field will be in this direction, and electric field, you know, will also be in this direction when E is negative, when x is negative, I'm sorry. So then you have a cylinder like this. The cylinder's length is 20 centimeter, and the x position above the origin is, this is minus 10 centimeter, this is plus 10 centimeter, both the ends. And you know, you have an area vector here and area vector here, because that's the area you have to take into account, because electric field is emerging like this. The surface has to be normal to the electric field. The electric field is emerging like this. So these are the two surfaces you have to take into account. This is the ds vector, which will also be normal, and the ds vector will also, electric field and the ds vector in both the cases are parallel to each other in this case. Unlike here where there was anti-parallel, in this case that was anti-parallel, here it is not, because they've said that electric field for negative x is negative, for positive x is positive, so they end up getting both parallel. And so then the flux in the left side is E dot ds cos 0, because, and on the right side, flux on the right side also E dot ds cos 0 only, cos 0 is just 1. You know what is electric, it's 200 I, and ds vector is just the surface area. Has the radius of this cylinder been given? The radius is given to be 5 centimeter. So you can write ds to be pi r square, and the electric field to be 200. It's actually minus the electric field. Okay, one second. This is EDS. Okay, it is. It may be specified as minus 200 I, but the ds vector is also in the negative direction. The electric field is also in the negative direction, and the ds vector is also negative in direction. So to put together, EDS will not be negative. So you just have to write pi r square cos 0. So then therefore, electric field's value is just 200. Don't write negative sign there, because you know it's parallel, so the positive answer only will fetch you. Pi r square will be along okay, pi r square, you know, ds vector is along negative x direction, minus I. Electric field is along minus I direction, and I square is 1, negative positive, so 200 pi r square. So then the calculation of this will be 1.57 Newton meter square per coulomb, and the flux on the right, as usual, you know, 200, and ds is also pi r square, the same value, but it will be along positive x direction. The flux will be along the negative x direction here, and this flux will be along the positive x direction. Yes, and so then this calculated value also will turn out to be 1.57 Newton meter square per coulomb square. The net flux will have to be added, so you just have to add these two flux, and so then you will get double the value, right? But you know that there will be no flux on this top. Why? Because electric field is like this, normal to the surface is like this. The angle between them is 90, therefore the flux is 0. And here also the ds vector is like this, electric field is like this, 90 degree, the flux is 0. or the flux is possible only on the right, the circular parts, and so the net flux therefore can be calculated. Are they asking for what is the net flux through each flat face? Yeah, we have done that. What is the flux through the side of the cylinder? That's 0. What is the net outward flux through the general cylinder? You have to just add these two. So it will be double, which is 3.14. The net flux will therefore be 3.14 Newton meter square per coulomb. And the next is by Gaussian's theorem, the net charge. Whenever they ask you charge, flux is equal to Q by epsilon naught. So Q is equal to flux into epsilon naught. Flux itself is 3.14 into epsilon naught is 8.854 10 to the power minus 11. So 8.854 10 to the power minus 12. And therefore its value itself is 3.14 Newton meter square. So what is it? Coulomb. So it's just a charge. So it's just coulomb. 3.14. No, the calculation will lead to 2.78 into 10 to the power minus 11 coulomb. Okay. 8 epsilon naught is 8.854 into 10 to the power minus 12. I hope I have written the same value everywhere. Just check that out. Okay, so then now not use it anywhere. Okay, so coming back to next sum, this is very very important. Cylinder and cube sums are really really important. The next is this example 67. Example 67 is very important. S1 and S2 are two concentric spheres enclosed. Okay, I hope I have not passed it. Okay. Two concentric spheres S1 and S2 enclosing the charge Q and 2Q. Can you see this? There's a sphere here which is enclosing Q, another one where there's a 2Q here. There's a surface S1, there's a surface S2, and this radius is R1, this radius is R2. What is the ratio of the flux through S1 and S2? Flux through S1, the flux will be because of the charge enclosed always. For the surface S1, it will be flux is equal to that Q by epsilon naught. Okay, for the surface 2, this is for surface 1. Surface 2 is enclosing two charges, that Q and 2Q. So it will be 3Q by epsilon naught. So then the ratio between them will be flux 1, flux 2. Okay, so flux 1 by flux 2 itself is Q by epsilon naught by 3Q by epsilon naught. So therefore it will be 1 by 3. Okay, next question is, if the medium of dielectric constant K is introduced between the space of inside S1, you're going to insert a dielectric constant K inside this. Then the flux through S1 will become K, flux through S1 will become Q by K into epsilon naught. That's only difference, right? So that's all. That's the answer for this in case MCQ comes. The flux through S1 does not change with supposing the next part of the question is you're going to introduce a dielectric between this surface. That will not, what will be the flux on due to S1? That's not going to be affected by dielectric which is outside of it. The dielectric medium is not inside of S1. The flux through S1 does not get affected by the dielectric medium which is only present inside of S2 and outside of S1. So then therefore it's not going to affect it. Okay, so that's what it is. I've completed most of the sums that's given here. Next is the proof for Gaussian's. There are lots of proofs for Gaussian's theorem, and I'm going to continue that. I'm thinking whether I should continue in this video or in the next video.